Okay, so we've got, I'm just going to do something on uniform linear acceleration here. Now, we know that speed is equal to distance divided by time. We'll be using this a lot for these questions. Now, velocity, the only difference between velocity and speed is that velocity is speed with a direction. So, now, for constant uniform acceleration, what happens is the speed changes. So that we have different quantities: time, acceleration, initial velocity, final velocity, and displacement. So the distance the particle travels. And we've got these units here for these quantities as well. Now, when an object is moving at a constant velocity, you can just use this equation here. If it's moving at a constant speed or a constant velocity, this is the only equation that you use. When an object is moving with uniform acceleration, the speed is changing, so you're going to have to use 3 equations. And one more important point is that negative acceleration is deceleration, and when it's positive, it's acceleration. Now, acceleration is also linked to force. We'll do that later on. So this topic is about any particles which move in a straight line and accelerate uniformly. It does come into this that sometimes you could have just a section where there's constant velocity as well. So I should probably include that there as well. Just that, so you'd be using the speed is equal to, or velocity is equal to distance over time for some sections of this. Okay? Now we're going to be looking at time-speed graphs and problems involving 2 particles. These are the 4 equations that you can use when you've got constant acceleration. Now they're on page 50 of the log tables as well, the formula book, so you don't have to learn them off. Probably doing them often enough that you will learn them off. It just happens. Now, when you're doing these questions, it's a good idea to write out a table. Now, I wouldn't write in these values each time. I've just got them here to show you. You write in your 5 variables: acceleration, initial velocity, final velocity, time, and distance. And you have your units, and then you can fill in your values and find out what they're looking for. An example here would be if you have a runner. Now, if this runner is travelling at an acceleration of 2.3 meters per second squared, initial velocity of 0, for a time of 2 seconds, and you could be asked for what is its final velocity or what is its distance. Now, for these, you use all those equations that we saw a second ago. I've done numerous examples. They're on the website as well, so I'm not going to spend time working this problem out. If you want, just pause it, give it a go yourself. What I want to think about here are distance-time graphs. Now, these would have been covered in your junior cert paper, where you've got time on the x-axis and distance on the y. Now, what this graph shows is that for a set amount of time, this body is going a set of distance. This is a graph for constant velocity. So, let's say if that's a 5 seconds there, every 5 seconds it could be travelling 10 meters. So you know, after 10 seconds it's gone 20. After 30 seconds, or this would be 5, 10, 15, 20, 30, 40 seconds here, it would have travelled 40 meters. Okay? Now this is, it'd be more than 40, it'd be 80. If it's 10 meters in 5 seconds, it'd be 40, it'd be 80 meters in 40 seconds. So a distance time graph you've done in junior cert, when it's a straight line, you've got constant velocity. Now, when it's like this here, you'll see that every section of time, it's going a little bit further than it did the previous second. So at this time, at the start, it's barely moved at all in one time. It's barely gone any distance. While up here, if you look at this bit here, in that little time frame there, it's actually travelled a big distance. So every time it moves a little bit, its velocity, or the change in distance, is getting bigger. This is a graph for acceleration. Similarly, this one here, as time goes on, it goes a little bit less distance. So this is a graph of deceleration. Now these are the graphs from your junior cert. You would have seen them hopefully in your junior cert science course. Now when we look at velocity time graphs, And these are the ones that we'll be doing, that we can really see. We can do a lot of interesting things with them, and I'll go through it with that 2010 question in a second. With a velocity time graph, what it shows when you've got a straight line like that is that the body is accelerating. So every few seconds its velocity is increasing. And I'll just keep on. So, but when you've got this, when a velocity time graph, now they never really come up, but when you've got a velocity time graph like this, the acceleration will be changing, and this one, the accelerating would be getting slower. What I'm interested though are velocity time graphs like this here. So let's say we've got a period of motion where the velocity accelerates. Then what's happened when it goes straight across here, it's moving at constant velocity. And then here we've got a moment where it's moving, decelerating for a period of motion. Okay? Now, 2010 ordinary level question. We've got a car travels along a straight road. It passes point P at a speed of 12 meters per second, then accelerates uniformly for 6 seconds to a speed of 30 meters per second. Now, on our graph here, we'd have, it starts off at 12 meters per second and accelerates uniformly to a speed of 30 meters per second. So this point here will be 30 meters per second. I'll go through why I'm doing this now in a second. Next, the car travels at a constant speed of 30 meters per second for 15 seconds. So I could mark this off as well. This would be time is equal to 0. This would be time is equal to 6. Okay, everybody with me so far on this? The next bit then is it travels at a constant speed of 30, so the velocity isn't changing. It goes like that up until this point here, which is at t is equal to 15 seconds. Oh no, it's for 15 seconds, so the time would actually be 21 seconds there. And I'll just go back to this here. So then we're told it decelerates uniformly to rest at a point Q, and the car travels 45 meters when decelerating. So I'll just go back to that point there. We know it decelerates then to this point here, and we know that it travels a distance of 45 meters during that deceleration. We're given the time for this section here, but we're not given the time for this bit here, we're given the distance. Now, to solve this problem, the first part of the question asks us to find how much acceleration it's got. Now we've got v is equal to u plus at. We know the final velocity is 30, we know the initial velocity is 12, and we know the time is 6 plus a times 6. Subtract 12 from both sides, we get 18 is equal to 6a. Acceleration is equal to 3 meters per second squared for that first section. We're also asked to work out the deceleration for this section here. So that's part 1 of that question done. Part 2 then is the deceleration, this section here. Now we know that the initial velocity u is 30 meters per second. It's very easy to read off the graph there. That's the initial velocity for this section. Our final velocity v is equal to 0 meters per second. We're looking for the a, and we're given that s is equal to 45 meters per second. 45 meters. Again, for this here, what we want to do is we have our 4 equations, and I'll just write them here. V is equal to u plus at. V squared is equal to u squared plus 2as. S is equal to ut plus 1/2 at squared. So we don't have time. We've got u, v and s. We're looking for acceleration, so it's going to be this equation here, or it'll be deceleration. So I'll just sub the values in there. We've got 0 is equal to u squared, which is 30 squared, plus 2a times 45, the distance. So 30 squared is 900 plus 90a. Rearranging this, we get 90a is equal to minus 900. Our a is equal to minus 10 meters per second squared. That's the second part there. So we've got the 2 parts of this, those 2 first parts worked out. Now we don't need the velocity time graph for those 2 first parts. In fact, they don't do anything for us. What I want to say about the velocity time graphs is that why we use them, and I'm just going to see if I can get this in a different colour. is that if we get the area underneath this graph here, now this bit here is easy because it's just a triangle, so it's going to be a half the base by the perpendicular height. This is just a rectangle here, it should just be length by breadth. This here, you'll have to do a little triangle and a rectangle to get that bit. Rectangle there and triangle there. If you work out the area underneath the graph here, it tells you something. The area underneath a velocity time graph, velocity in that axis, time in that axis, the area under the graph is equal to the distance travelled. Travelled. I might have to delete on this. So I'm just going to go back there for a second to the previous question here. Now it asks us to find the distance from P to Q. There's two ways we could do it. We could work out the distance using the formulas for each of these sections, split it up. The other way is that if we have a good velocity time graph, we just get the area underneath that graph. Literally, I'll do it for this bit here. We know that the distance from here to here was 15 seconds, and the height there is 30. 15 times 30 is this here. 15 multiplied by 30 tells us the distance travelled in that section there. Similarly, you could do it for that section and that section. Now, I might leave it at that just for a moment, so we can escape out of it. And you can probably just try to finish off this question from that.